Hello, everyone. Good to meet all of you virtually. So I'm recording this video at my nighttime, and it will be shown to you in your day, in my daytime, which will be evening to most of you in the UK. So that's kind of interesting. My name is Sheroz Khan, and I'm a scientist at KITE Toronto Rehabilitation Institute in Canada. I'm also cross-appointed with the Biomedical Engineering Department at University of Toronto. And today I'm going to talk about a very interesting and one of the first pilot study to detect agitation in people living with dementia using multimodal sensors. And we will show our preliminary results on using machine learning techniques and some of the lessons learned during this very, very exciting study. So to give you the context, we all know that the world is aging. As of now, 1 in 10 people are over 65 years or older. In just 3 decades from now, that number will increase to 1 out of 5. So that's a significant change. And aging comes with its own complexities and you can say some problems, so which can be both physical and cognitive. So for example, as you age, you become more frail. That could lead to falls. That could also be related to lack of physical activity and so on and so forth. A major problem is actually dementia that comes as you age. Now, dementia is an overall term for diseases and conditions characterized by a decline in memory, language, problem-solving skills, and social abilities that affect a person's ability to perform activities of daily living. In extreme cases, a person may even forget who they are. They may not even remember or recognize their immediate family members. And that can actually cause a lot of distress to them. Now, dementia, apart from these problems, it can actually incur a huge cost on the healthcare system. By 2050, we will have more than 130 million people living with dementia. Currently, the cost is around $1 trillion US dollars. Now, as I said about dementia, due to the onset of dementia and as dementia problem progresses and becomes more severe, people may often exhibit these behavioral and psychological symptoms of dementia, such as depression, irritability, anxiety, and agitation. Agitated and aggressive patients with dementia can actually harm themselves. They can harm other patients if they are living in a long-term care facility, their caregivers if they're living in the homes, or the staff if they're in the nursing homes. And there have been actually, unfortunately, some deaths reported in the media as well due to these agitated and aggressive episodes. So for example, in British Columbia, during the period of 2012 to 2016, 16 deaths were actually attributed because of these agitated and aggressive behaviors among the patients. Now, the traditional way to gauge agitation and aggression is actually the clinical way of doing it, and which is mostly behavioral. So there are some standard clinical scales, and clinicians who are trained at it, they can observe the person and they can, they can actually give a score as to what level of agitation or aggression the person is having. However, there's a problem with that kind of method. First of all, it is very time consuming. Somebody has to monitor, somebody has to look at you all the time. Those are prone to errors. Those are can be very subjective, right? So, and a fundamental problem from our perspective in these observational methods is that they cannot predict the onset of agitation or aggression, right? So the question here is that can we use technology, can we use AI and machine learning to detect and, if possible, predict these agitation and aggression behavior? So this was our research question. Now to answer this research question, we actually proposed this study. We got funding to start this study, and we ran this study in the specialized dementia unit at Toronto Rehabilitation Institute. Now I'm going from this point onward. I'm going to talk a little bit about the study that we did, the setup, and some of the information about it. So the central hypothesis was that that using multiple sensors, we should be able to pick up these agitation and aggressive behaviors more accurately. And to do that, we actually proposed this novel multimodal sensor setup that we installed at the specialized dementia unit at Toronto Rehab, which included 15 cameras that were installed in the common areas of the dementia unit. Then we had, as you can see in the screen number 2, which is a sleep mat that goes under your mattress, and it can monitor your sleeping patterns, respiration rate, breathing rate, and so on and so forth. Then we also use some ambient sensors such as number 3 and 4, which are motion and door sensors to understand their movement. And the most important one is this wearable device. It's a commercially available device. It's called Empatica E4. It can actually collect your raw sensor data. Now it can collect motion and physiological sensor data, and I'm going to talk about that a little bit later about it. Now we ran this study for 2 years and 1 month. So that's 25 months. That's a long time. From November 2017 to November 2019. And we trained staff and nurses to record the agitation and aggressive behaviors in a particular manner in their nursing charts. We asked them to highlight if any incident happens with the green dot. I mean, these green dots we literally bought from dollar stores, and we gave it to them. So whenever there's an incident, they will stick these dots on the nursing chart, so it's easy for us to review and annotate the data. We asked them to mention the start and end time of these incidences, the location where it happened, and what was the context of this behavior, like what was the nature of the patient, what caused those incidents, if that information is available. Very early on in the study, we actually realized a problem, and the problem was that the door and motion sensors were giving a lot of noisy data. And partly the reason was that, so we installed these motion and door sensors in the toilets and on the door of the toilet. And the idea was, like, if a person is agitated, they would be just wandering and walking around restlessly. But then we realized very soon that these motion sensors would pick up any person, any other patient, staff, visitor, doctor, clinicians, whoever was present at that moment in that area, they would pick it up. So there would be a lot of false alarms, and there was no way to know if the sensors are picking up the designated patient in the study, or the person who is in the study, or others. So even though we collected this data, we collected the data for all the patients, we eventually decided not to use the data. Sleep mat data is another funny story, because after 10 patients' data, when we collected 10 people's data, the company was actually who provided these sleep mats was acquired by another company, and their business direction changed to consumer products, and they started building commercial mattresses, and they stopped actually giving support to us. So we never got the data from them after that. So we decided to analyze this data separately. There was another issue with sleep mat data, because it was not tied to a person. So anybody who is sitting on that bed, for example, we would still pick up the physiological signals, and of course a lot of noisy data in that case as well. At the end, we were with the full support of the nursing staff, we were able to get 74% of agitation levels fully reported. That was awesome. That was great. I mean, I think our nurses in the unit, they did a fantastic job. We know they're busy. We know they are overworked. Most of the time they are looking at so many patients, but they did a fantastic job. 75% of the data, and mind it, this study was running for 2 years, right? Despite their best effort, there have been some cases where some of the start or end times were missing. So in the nursing chart, you would see, oh, John started this agitation episode at, let's say, 9:40 a.m. and then there's no end time. And we also believe that there may be there's a possibility that there may be few unreported events or very short events that a nurse might not be able to capture. So we added another layer of data quality checking, and that is very important from machine learning perspective, because if we do not have a good label data, then it is really hard to make sense from it. So we added another layer of data quality checking, and various research assistants would go and they would look into those cameras in that reported time. So just to give you the context, so we were recording data from 15 cameras, 16 hours of the day, not during the night shift, due to some consent issues, and I'll talk about it at the end of my presentation. And we did that for almost 2 years. So if somebody has to look into these videos, that would take them 2 years to just view those videos. So we use the start and time information from the nursing chart, and that helped us to narrow down the videos that we wanted to look. So adding this actually layer helped us in refining or fine tuning the labels. So for example, the nurse is saying in the nurse chart that John started agitation at 9:10 and then the agitation ended at 9:40. But when we look into the video, and these researchers, these RAs are clinical people, so they know what they're doing, right? So they would refine and they say, no, it's not 9:10, it's perhaps 9. It is actually 9:13 to 9:37. So this way, we are actually getting more accurate data, and that was very time consuming. Anyway, so there's some information about this data. Now we actually recruited 20 patients in this study. 3 did not show any agitation. So the data that I'm showing in this table is actually belonging to the remaining 17 patients. Mean age 78 years with a standard deviation of around approximately 9 years. Average range from 65 to 93. So you can see a broad spectrum. Gender 7 males, 10 females. Number of days 600 days of data collection. Now you would say no, I said it's 25 months, so the number of days should be more, right? But then for some days for some days we may not have a participant, and technology fails, so our cameras failed once, and there was a problem with the DVR. So there were some days where we were not able to record due to technology, or due to recruitment issues. Overall 239 agitation days, and agitation day is defined as a day where at least one agitation event happened, and total reported agitation events are 411. So one particular agitation day can have multiple agitation events, and then out of which 305 are fully labeled agitation events, which is around 74%, as I said, which I think is phenomenal, believe me. Some more information about the data. So one person was recruited for around 62 days. So because we set our protocol that the maximum will be around approximately 2 months, we will recruit a person, and one person was only there for 7 days. One particular person actually showed 66 agitation events, and there were 3 patients who showed 0 events. So as per the protocol, if a person is not showing any agitation behavior for 2 weeks, we remove them from the study. Interesting thing is that the duration of these events varied a lot, from 1 minute, very small burst of agitation, to 3 hours of agitation. And I can tell you a lot of stories about the different behaviors of agitation. I mean, the behaviors were also different. I mean, duration is one thing, and then behaviors were entirely different. So to give you a little context, so we had one person, one lady, very nice, sweet lady, that she used to walk a lot in the unit, and when she's agitated, she would walk more. Now, to me, I'm not a clinical person, it's the same thing, but the nurses would know that she is agitated. Now, there was another gentleman who would just sit on the chair, and when he's agitated, he would get like really, really angry. And it's like he would be like all pink and blues and red, it's like very, very angry, but he would just sit on his chair. So different types of behaviors. There was one person who used to, kick and punch the nursing door. So very motor agitation, very, physically you can actually see that kind of behavior. Okay, moving on. So raw sensor data. So as I said, we collected from this Empatica E4. So the results that I'm going to talk about and show are actually coming from this wearable device. It's a multimodal or multi-sensor device. So we can get accelerometer readings from it. So that can help us in identifying motor agitation and physical aggression. Then we can, from this device, we can actually get raw sensor data for blood volume, pulse, that can help us in getting heart rate and other kind of information related to heart and the electrodermal activity, the little electrical thing that happen on your skin, and skin temperature. And these physiological indicators can help us in estimating some of the non-motor agitation. So for example, this person who was just sitting but angry and shouting, but unfortunately, due to ethics restrictions, we were unable to record any speech data, so we are only relying on these 4 sensing modalities. Now, when you look at the sensor data, at the top is the BVP, sorry for the poor resolution. At the top is the BVP, and then you have accelerometer, heart rate, and temperature. Just looking at the raw sensor data, it is really, really hard to make sense from this data. So these bars that you see are actually showing an actual incident of agitation. You can see some peaks happening in blood volume, pulse, and accelerometer and heart rate, but then there are other peaks as well at different parts of this. Maybe the person is just walking, or maybe their heart rate increased for some reason. We don't know. So just by looking at the raw sensor data, it was really, really hard to do so. And as you can see, our temperature does not change much, right? So most of the time it's kind of constant. So of course, we have to come up with a more sophisticated approach, and this is a typical machine learning kind of pipeline that we followed in this work. We filtered the sensor data, then we extracted 37 time and frequency domain features. Actually, we extracted more features, I think 67, but then we removed most of the correlated features. So we end up with 37 time and frequency domain features, and then we applied standard machine learning techniques on this combined data for everyone. We actually extracted sensor data for 1 minute, 3 minute, and 5 minute windows. Those are non-overlapping windows, and these are the features we extracted from each sensor. So from accelerometer, we extracted 10 features, from BVP 17, EDA 7, temperature 3. So total of 37 features. So these are the final 37 features we worked on. Now, to give you a little bit of more idea, so extracted features actually look visually a little bit better than the raw sensor data. So just to give you an example, so these red bars are the time when the person when the person had agitation, right? So you can see from accelerometer, we extracted, for example, this maximum of trigger energy. We see this peak, and then the person has agitated, and similarly in EDA and BVP, we see some of these peaks. But the problem is that there are similar peaks at other places as well. So this is actually a sort of an indication that individual sensors may not be very useful, and they may give us a lot of false alarms. So the next logical step is to combine all of this data together and to see if we can do better with a multimodal sensor kind of approach. We also did another layer of feature ranking, where we extracted, based on the feature ranking, we extracted 15, 20, we extracted features containing 70%, 80%, and 90% of the information, and we extracted the corresponding features, and then we tried to build models on them to understand, can we do better with less features or more features, that kind of analysis. So these are the different number of features that we actually extracted using like the top 10 ranked features, then 70%, 80%, and 90%. And as you can see, the interesting part is that accelerometer features were actually selected by this feature ranking algorithm. And I think the interesting part is that why accelerometer features are extracted. And I think the reason is that a lot of these agitation behaviors are actually motor agitation, where a person is like really, really agitated and waving their hands and kicking and punching, things like that, which accelerometers are very good and meant to pick up these things. But at the same time, blood volume pulse and electrodermal activity also were important. Temperature features, not, because most of the time our temperature, like as I said, does not change much, and they did not, and they were not picked up by this algorithm, right? Now, this is some quick comment about the experimental setting. So we tried standard classifiers like logistic regression, SVM, random forest. Now this data is very skewed. More than 96% data is normal events. And then I'm talking about this one window now, because we found out that 3 minutes and 5 minutes windows were not performing good. So the results I'm going to talk about from this point are actually related to the 1 minute window. So when we extracted 1 minute windows, we found that 96% of the data was normal, and more than 3% is actually is agitation. So the data is very skewed. So we also employed a cost. We added cost when we were training these classifiers. We also did an additional experiment of randomly labeling the data to understand, are we able to confuse the classifier or not? Because if we are not able to confuse the classifier, then we are not doing anything good. Internal two-fold cross-validation for parameter tuning for these classifiers, and then we did a two-fold cross-validation to evaluate the classifiers and area under the curve of ROC curve. AUC of the ROC curve was used as a performance metric. This is the table. Lots of numbers, confusing, I know. So, but we'll make it easy for you. You see, so we have these, the first column, of course, are the features, the single features, when we have just accelerometer, BVP, DA, and temperature, and then we have 70%, 80%, 90%, and 100% of the features, like combined, all of them. The second column is the number of corresponding features, and then the classifiers. So the big message, do not look at this table. The big message is that logistic regression and SVM did not work well at all. So I'm going to remove them. The next is, and then of course, random forest also worked, but the original random forest did not work. So but the cost version of random forest worked much better. So I'm going to remove all of them. We also did this random labeling with the random forest, and we see that we were able to get 0.5 AUC. So our methodology was right. So I'm removing that. So this is the most important result that we get. And if you see the results above this dashed line corresponding to signal to single sensors, you will see that the results are around 0.6, and temperature sensor was actually performing the worst. But when we look at the combined, the results from these combined features from all the sensors, when we use these multimodal sensors, we see an increase in the AUC. So from 70, 80, 90% to when we have all the 100% features, we were able to get 0.82 AUC, which I think was a very encouraging and very exciting result for us. And this also actually shows that the utility of multimodal sensors, and that it can capture different types of behaviors that we cannot and we may not be able to detect by individual sensors. Here it is, 0.82. Okay, so now I'm going to conclude this presentation, and of course most of the things I discussed, but just to summarize, for this problem, for detecting agitation in people living with dementia, multimodal sensors gave significantly better results in comparison to single sensors. Accelerometer, blood volume pulse, and electrodermal activity turn out to be the most informative features in comparison to temperature. And as we saw before, that a majority of the selected features were actually coming from accelerometer, and that can be explained that a lot of these behaviors are physical aggression or motor agitation. But there are different types of other agitation. For example, verbal agitation that we cannot pick up because we did not have that sensing modality. And of course, these results are based on the fully labeled agitation events. There are still some agitation events that are not fully labeled, and we are currently working on them, and to come up with different types of scenarios, different types of machine learning approaches, and I'm going to talk about them in a minute about that. And you might say, like, when we had the second layer of review of research assistants looking into the camera readings, why they were not able to label the data even if it is missing in the nursing chart. And the reason is that the cameras were only placed in the common areas, in the hallways, dining area, entertainment room, but not in their rooms. And if an agitation is happening inside the room, and if the start or end time is missing in the nursing chart, then there is no way for us to go and look into those videos and determine when the person was agitated or when they stopped being agitated, right? So we have to live with the fact that there will be some unlabeled data in this data set, and we'll have to come up with alternate strategies to handle that. Now, before moving on to the expected future work slide, let me take a moment on the lesson learned. This was a long study. 2 years is a long time. Many people actually graduated during this study. I became a scientist from a postdoc when I started this study. I was a postdoc initially, and then I became a scientist at Toronto Rehab. People gave birth, so it was a long time. And we learned lots of lessons in this study. First and the foremost, the massive data. We were actually storing, when the study was on, 80 gigabytes of data per day, and we ran out of space. And we have to be creative. We have to come up with some schemes of, some actually ideas around how to transfer this data over the hospital network, store it in so not cloud, but like an internal cluster storage, and you cannot turn on and turn off because we were not, collecting the data at the night. So we have to come up with some other ways of automating the whole process. It was a nightmare, believe me, and then technology failed. So all of those things. So in the end, we end up with, I think, more than 30 terabytes of data, and we have to pay a lot of dollars. I think thousands of dollars to store this data internally. Another problem was this distributed storage. So different sensors were sending data at different places. So the watch data was going to the watch cloud, and then the camera data was going to the hospital network, and these image sensors, the smart mat was sending data to their cloud, and the other motion and door sensor we were getting through the email alerts. So it was a nightmare to combine all of this sensing modality at one place, and actually that was a bigger challenge, and it took a lot of time to actually make sense from all of this data. Expensive devices. This watch is actually more than $2,000, and we got like three watches, initially three, and then one was lost. Nobody knew what happened to that. The theory that goes around is that maybe the patient put it in the toilet and flush it because it's of no use to anybody, right? So expensive devices. And there's an enormous cost in installation and uninstalling the devices, because these are very sensitive units. You cannot just go and put all your hardware. Again, thousands of dollars. Staff consent is a major issue. There are more than 40 active staff who work on this unit, and some, I think one or two are not comfortable recording, turning on the camera during the nights. So they said no, and that is why we had to turn off our recording for the night. So we have no data for the night. Even though most of the staff are supportive, and we're very thankful to those who said yes, and because of their continuous effort, we were able to collect this data, and we have this plethora of data to analyze. Another limitation from the computational side is most of the processing is offline. Of course, this is a huge amount of data, so you cannot do, I mean, you can do online, but we did not have that infrastructure at that time. So all of this analysis is actually offline. Now, moving forward, like this is great amount of data that we have. And as I already mentioned, there are lots of future directions that we have right now. And there's a lot of things, there are a lot of things that we can do. One of the first and the foremost is the personalized models. Like I gave you example about these 2 or 3 patients that we had. We had 20 patients, 20 different personalities. Everybody had a different behavior. And we actually did recently these experiments on, leave one subject out kind of experiments where we train data on n-1 people and test on the nth person, and our models are not performing very well. And I think one of the reason is that everybody's behavior is very different, so it's very difficult to generalize those kind of models. So perhaps the right way to look at this problem is to develop individualized and personalized models and to build these predictive models. As I said, a lot of data is unlabeled, so we might have to look totally out of the box and maybe look into other modeling strategies such as positive unlabeled data learning techniques. The data is skewed. We have only included the agitation days. If we include normal days, then the ratio of these agitation events will be even smaller. Right now, it's around 3.25%, but I'm sure it will become, even smaller, maybe less than 1%. So maybe we need more anomaly detection kind of approaches, or one class classification of approaches. And for those who are thinking why these guys are not using deep learning yet, so my answer is we are on it. We work in a clinical system, in a clinical setup. Our collaborators are clinicians, and to them, it is more important to first understand what is going on. We cannot just come up with a black box. Of course, deep learning models are also now getting more, interpretable with attention and all these kind of new methods that we have. But we wanted to create this baseline, and the purpose of all of this analysis is to build this baseline. And anything we do from this point on, we can always compare. So of course we are already working on some of very interesting deep learning ideas around it. You may also ask, like, oh, you have this huge amount of user data, what are you doing about it? So the good news is we actually got a Catalyst grant, and we are currently working on analyzing the data, and we are actually getting very promising initial results. And the good thing with this kind of approach is, like, you can visualize, you can see what is going on in a video, and we are actually able to identify some other risky or anomalous behaviors which were not even reported in the nursing charts. Because so that's very exciting work for us. And I think moving forward, like as I said, we had this problem of sensors sending the data everywhere and then offline processing. So I'm just tired of that, honestly, and I want to build a more scalable and a cloud-based kind of system where we can store this data at one place, and we should be able to build these models in the AI. So this is the work in progress, and we actually are working in this direction very actively. So this is all what I have to say. Before I conclude, this is our team, and I'm very thankful to all of the team members. Sophia, who's the postdoc who did this data analysis work. Dr. Andrea Ebony, she's our clinician, researcher, and scientist, very helpful, and we could not have done anything without her. Dr. Alex and Christine, both are other co-PIs and very supportive. Bing, very helpful in management of the overall study, writing the ethics, applications, and amendments all the time. Angel and Shu for reviewing these videos. We know this is a very hard job, but thanks again. And many other scientists, professors, whose name I cannot put in here, research assistants, interns, who have touched this study over this period of time. And Many thanks to all of us. A big shout out to Robin Shan, who was the nursing manager and who really helped us in facilitating this study. All the nurses, of course, thank you very much. And thanks to all of you to listening to this talk. And I'll be very happy to have to answer if you have any questions. Thank you.